16d to the power of 4 plus, when we multiply these two terms, what we get is a square minus 9d square, and when we multiply these two terms, we get a square minus d square. As we know that a square minus b square is always equal to a minus b into a plus b. Now, s is 16d to the power of 4 plus a square minus 9d square into a square minus d square. When we multiply both these terms, what we get is s equal to 16d to the power of 4 plus a to the power of 4 minus a square d square minus 9a square d square plus 9d to the power of 4. Now, when we add these two terms, we get minus 10a square d square, and when we add these two terms, we get 25d to the power of 4. So, s becomes equal to a to the power of 4 minus 10a square d square plus 25d to the power of 4. Now, this could be further written as s equal to a square minus 5d square whole square. Thus, s becomes a square minus 5d square whole square. That is, s could be written as equal to k square, where k is equal to a square minus 5d square. Thus, s becomes equal to the square of an integer. Here this is an integer, so s would be the square of an integer. And so we have proved that the sum of the fourth power of the common difference plus the product of any four consecutive terms of an AP is a square of an integer. So this was all about the arithmetic progressions. In this lecture we have seen what is an arithmetic progression, how to find the nth term of an arithmetic progression, how to calculate the sum of n terms of an AP, and what are some of the very important properties of an AP. In the next lecture we are going to study about geometric progressions. Hi students, in this lecture we are going to study about the second kind of progressions, and that is the geometric progressions. What exactly are geometric progressions? How to find out the nth term of a geometric progression? How to calculate the sum of n terms of a GP? Further, we are going to see what happens when the number of terms in a geometric progression becomes infinite, and also how to calculate the sum of all the terms of a geometric progression when the number of terms are infinite. Also, we are going to see a special type of series which is known as the arithmetico-geometric series. Now, what is that type of series and how to find the nth term or the general term of such a series? So, all these are the concepts that we are going to study in this lecture. Now, let us suppose that we are working in a biotechnology lab and we have been given a trough in which we have one bacteria cell. So, we can write this information as at t equal to 0, the number of cells equal to 1. In the next hour, we observe that the number of cells become double. That is, the number of cells become equal to 2 at t equal to 1. After 1 hour, the number of cells become 2. In the next hour, we observe that the cells double again. That is, they become equal to 4. So, the number of cells would be equal to 4 at t equal to 2. Again, in the next hour, they become double of 4. That is 8 cells. So, in the trough, we have got 8 cells at t equal to 3 hours. In the next hour, again, they become double of 8. That is, the number of cells become 16 at t equal to 4. And again, in the next hour, we observe that they become double of 16. That is, the number of cells equal to 32 after t equal to 5 hours. So, the question is, are these cells following some pattern? Can you tell me after 20 or 30 hours how many number of cells would you find in this trough? Now let's try to look at the number of bacteria cells and the pattern they are actually following. Initially we had one cell. We multiply this by 2 and see that the number of cells become equal to 2. In the next hour they again become double of each other. That is, we multiply 2 by 2 and so we get the number of cells equal to 4. In the next hour again they become double of 4. That is, we multiply 4 by 2 and get the answer as equal to 8 cells. In the next hour again they double and so we get the number of cells equal to 16. In the next hour again they become double and they become equal to 32, and so on. The series would continue. Thus what we can say is the number of bacteria in the trough follows a geometric progression. So the number of bacteria cells in the trough are actually following a geometric progression. But now what is geometric progression? So let's try to look at the definition of what exactly is geometric progression. So we can define this as A geometric progression is one in which the ratio of any term to its predecessor is always the same number. This ratio is called the common ratio. So, geometric progression is a one in which the ratio of any term to its predecessor is a constant number, and this number or this ratio is called as the common ratio. Let's try to understand this. Let us say that we have a GP or the geometric progression in which A1, A2, A3, A4 and so on up to AN are the n terms of this GP. Now if we multiply A1 by R, then we get A2. Similarly, if we multiply A2 by R, we get A3. If we multiply A3 by R, we get A4 and so on. And so here the common ratio is equal to R. We can say that A2 by A1 is equal to R, A3 by A2 is also equal to R, A4 by A3 is also equal to R, and this pattern follows throughout the series. And so here the common ratio is equal to R. A2 by A1 equal to R, A3 by A2 equal to R, A4 by A3 equal to R, and so we can say that AN by A of n minus 1 is equal to R. And so this is the pattern that a geometric progression follows. We have a common ratio over here. Now for a GP, let's try to see the formula to calculate the nth term. Let us say that the first term of this GP is equal to A and the common ratio is equal to R. So the first term is equal to A. Second term would be A into R. We simply multiply A by the common ratio, which is R. Similarly, the third term would be AR square. We multiply AR by R and we get AR square. The fourth term would be AR cube and so on. Thus we get nth term to be equal to A into R to the power of n minus 1. Thus the nth term of a geometric progression with the first term as equal to A and the common ratio equal to R is given by the formula A into R to the power of n minus 1. Here important thing to note is this is the nth term and the exponent of R is n minus 1, that is 1 less than n. So this is the formula to calculate the nth term of a GP. Now let's try to solve an IIT problem based on the above formula. If x, y and z are the pth, qth and the rth terms of an AP and also of a GP, then x to the power of y minus z into y to the power of z minus x into z to the power of x minus y is equal to option number A is xyz, option number B is 0, option number C is 1 and option number D is none of these. So in this IIT problem we have been given that x, y, z are the pth, qth and rth terms of an AP and also x, y, z are the pth, qth and rth term of the GP as well, and based on this we have to find out the value of x to the power of y minus z into y to the power of z minus x into z to the power of x minus y, and we have been given the four options. So let's try to see the solution of this problem. Given to us is that x, y and z are the pth, qth and rth terms of an AP. So we can say that x is equal to a plus p minus 1 into d, y is equal to a plus q minus 1 into d, and z is equal to a plus r minus 1 into d. Here we have taken the first term to be a and the common difference equal to d. We have simply used the formula for finding the nth term of an AP. From this what we get is x minus y would be equal to p minus q into d. We subtract this equation from this to get x minus y equal to p minus q into d. Similarly, we subtract this equation from this equation to get y minus z equal to q minus r into d, and we subtract the first equation from the third to get z minus x equal to r minus p into d. Thus we have got the expression for x minus y, y minus z and z minus x in terms of p, q, r and d. Now also given to us is that x, y, z are the pth, qth and rth terms of a GP as well. So x, y, z are also the pth, qth and the rth terms of a GP. So let us say that we have a GP in which the first term is equal to b and the common ratio is equal to r. Therefore we can write x equal to b into r to the power of p minus 1, y equal to b into r to the power of q minus 1 and z equal to b into r to the power of r minus 1. As x is the pth term of this GP, y is the qth term of this GP and z is the rth term of this GP. Now x to the power of y minus z into y to the power of z minus x into z to the power of x minus y could be written as b into r to the power of p minus 1 into y minus z into b into r to the power of q minus 1 to the power of z minus x into b into r to the power of r minus 1 to the power of x minus. We have simply substituted the value of x, y and z in this expression. Now when we multiply, what we get is b to the power of y minus z plus z minus x plus x minus y into r to the power of p minus 1 into y minus z plus q minus 1 into z minus x plus r minus 1 into x minus y. Further, we see that this becomes equal to 0. So this would be p to the power of 0. Similarly, we have got the value of y minus z equal to q minus r into d. So we replace y minus z by q minus r into d over here. Similarly, z minus x is nothing but r minus p into d. So we have replaced it here, r minus p into d. And similarly, we can replace x minus y by p minus q into d. When we multiply them and add them, what we get here is equal to 0. So x to the power of y minus z into y to the power of z minus x into z to the power of x minus y is equal to p to the power of 0 into r to the power of 0, and this is nothing but equal to 1. Thus we can say that option number C is correct. Thus simply using the concept of AP and GP, and that too the nth term of AP and GP, we have solved this IIT problem. Let's try to solve one more IIT problem, and this problem appeared in 2001. It says that let alpha beta be the roots of x square minus x plus p equal to 0 and gamma and delta be the roots of x square minus 4x plus q equal to 0. If alpha, beta, gamma and delta are in GP, such as geometric progression, then the integral values of p and q respectively are, option number A is minus 2 comma minus 32, option number B is minus 2 comma 3, option C is minus 6 comma 3, and option number D is minus 6 comma minus 32. So in this problem we have been given the two quadratic equations x square minus x plus p equal to 0 and alpha and beta are the roots of this equation. Also the second equation is x square minus 4x plus q equal to 0 and gamma and delta are the roots of this equation. Also given to us is that alpha, beta, gamma and delta are in GP, and we have to find out the integral values of p and q, and we have been given the four options. So let's try to solve this problem. Given that alpha and beta are the roots of x square minus x plus p equal to 0. Now this is a quadratic equation in which the roots are alpha and beta. We also know that sum of roots of a quadratic equation is given by minus b by a, and the product of roots is equal to c by a. In this equation, b is equal to minus 1, a is equal to 1 and c is equal to p. Therefore alpha plus beta, which is the sum of roots, would be equal to 1, and the product of roots alpha beta would be equal to p. Also we have been given that gamma and delta are the roots of x square minus 4x plus q equal to 0. Therefore the sum of roots would be equal to gamma plus delta, and that is equal to 4. And the product of roots gamma into delta would be equal to q. Now we have also been given that alpha, beta, gamma and delta are in GP. They are in geometric progression. Therefore we can take alpha to be equal to a, beta to be equal to ar, gamma to be equal to ar square and delta to be equal to ar cube. Here we have taken the common ratio as equal to r. Now what we do is we substitute the values of alpha, beta, gamma and delta in the equations to get a plus ar equal to 1 or a into r plus 1 equal to 1. So that is alpha plus beta is equal to 1. Also alpha into beta is equal to a into ar, which is equal to a square r, and that is given to be equal to p. Therefore a square r is equal to p. Similarly delta plus gamma is equal to ar square plus ar cube, and that is given to be equal to 4. Therefore if we take ar square common, we get ar square into r plus 1 equal to 4, and let us say that this is equation number 7. And the last equation is gamma into delta is equal to q. So ar square into ar cube would be equal to a square into r to the power of 5, and that is equal to q. Let us say that this is equation number 8. Now what we do is we divide equation 7 by 5. When we divide this equation by 5, what we get is r square equal to 4. Why? Because a and a gets cancelled. and also r plus 1, and r plus 1 gets cancelled. What we are left with is r square, and this becomes a equal to 4. Therefore r would be equal to 2 comma minus 2. And when we substitute the values of r, we get the value of a, and when we substitute the values of a and r in this equation and in this equation, we get the values of p and q. So solving them, we get p equal to minus 2 and q equal to minus 32. And so what we can say? We can say that option number A is correct. Thus the value of p is equal to minus 2 and q is equal to minus 32. Now the next part is sum of n terms of a series. That is, if the n terms are in a geometric progression, then what is the sum of all these terms? Let us say that Sn, that is the sum of n terms, is equal to a plus ar square plus ar cube plus a into r to the power of 4 and so on up to a into r to the power of n minus 1. We take a as common, and what we get is Sn equal to a into 1 plus r square plus r cube plus r to the power of 4 and so on up to r to the power of n minus 1. And let us say that this is equation number 1. What we do is we multiply both sides of this equation by r. R is the common ratio. So what we get is r times Sn equal to a into r plus r square plus r cube plus r to the power of 4 and so on up to r to the power of n. And let us say that this is equation number 2. So we have simply multiplied equation number 1 by r, and so we get equation number 2. And what we do? We subtract equation 2 from equation 1. So what we get is 1 minus r into Sn equal to a minus a into r to the power of n. Why? Because this becomes ar, this becomes ar square, this becomes ar cube. This gets cancelled with ar square, this gets cancelled with ar, this gets cancelled with ar square and so on. Only we are left with a and a into r to the power of n, this term. Therefore this would be equal to a minus a into r to the power of n, and let us say that this is equation number 3. Now we divide both sides by 1 minus r, and so what we get is Sn equal to a into 1 minus r to the power of n divided by 1 minus r. And thus what we get is Sn equal to a into 1 minus r to the power of n divided by 1 minus r. And this is the formula for the sum of n terms of a series. Thus we can say that if we have a geometric progression in which the first term is a, the common ratio is r, and the number of terms is n, then the sum of all these terms is given by the formula a into 1 minus r to the power of n whole divided by 1 minus r. Now what happens when r is equal to 1? We've seen in the formula that the denominator contains 1 minus r. So if we substitute r equal to 1 over there, then we get Sn as an indefinite quantity. So what happens when r equal to 1? Now ignore the formula for some time and look at the basics. Your Sn is equal to a plus ar square and so on up to a into r to the power of n minus 1. Simply substitute r equal to 1 in this equation to get a plus a into 1 plus a into 1 square plus a into 1 cube and so on up to a into 1 to the power of n minus 1. Now we know that 1 to the power of n is always equal to 1. Therefore Sn would be equal to n times a, as there are n terms. Therefore Sn would be equal to na. Thus when r is equal to 1, we get the sum as equal to n times a. Now based on the above formula for the sum of n terms of a GP, let's try to solve an example. Sum to n terms the series 6 plus 66 plus 666 plus 6666 and so on up to n terms. So again let's look at the solution. Let us say that Sn is equal to 6 plus 66 plus 666 and so on up to n terms. Now we take 6 as common, and what we get is Sn equal to 6 into 1 plus 11 plus 111 plus 1111 and so on up to n terms. Further, what we do is we multiply and divide by 9. So we multiply and divide the RHS by 9 and get Sn equal to 6 by 9 into 9 plus 99 plus 999 and so on up to n terms. If we multiply this expression by 9, we get this expression. Now we can further write this as Sn equal to 6 by 9 into 9 could be written as 10 minus 1. Similarly 99 could be written as 100 minus 1. 999 can be written as 1000 minus 1 and so on up to n terms. Now we can further write this as Sn equal to 6 by 9 into 10 plus 100 plus 1000 plus 10,000 and so on up to n terms minus 1 plus 1 plus 1 up to n terms. Now 10 plus 100 plus 1000 plus 10,000 and so on is a geometric progression. We see that the common ratio here is equal to 10 and the first term here is equal to 10. So we can write this as, now 6 by 9 is nothing but equal to 2 by 3. So Sn would be equal to 2 by 3 into, we use the formula that we have just studied, that is the sum of n terms of a GP, and get 10 into 10 to the power of n minus 1 divided by 10 minus 1. This becomes n minus n. So this further becomes Sn equal to 2 into 10 to the power of n plus 1 minus 10 whole divided by 27 minus 2n by 3. Thus the value of 6 plus 66 plus 666 up to n terms is equal to 2 into 10 to the power of n plus 1 minus 10 whole divided by 27 minus 2n by 3. Now we have seen about the geometric series in which the number of terms are finite. But now what happens if the number of terms of any geometric series is infinite? So let's try to study that. We know that the formula of Sn, that is the sum of n terms, is given by a into 1 minus r to the power of n whole divided by 1 minus r. Now this could be further written as a by 1 minus r minus a into r to the power of n divided by 1 minus r. Now if there are infinitely many terms, then n would tend to infinity because n denotes the number of terms, and if there are infinitely many terms, then n would tend to infinity. Also, if we have modulus of r less than 1, that is r lies between minus 1 and 1, then r to the power of n would tend to 0 because n tends to infinity. So this term would be very small, r to the power of n would be very small, and so it would tend to 0, that is it would be very close in value to 0. And so in this formula this term would tend to 0 because n tends to infinity. Now when n tends to infinity, this term would tend to be 0, and so what we get is the formula of S of infinity, that is the sum of infinite geometric series, is equal to a divided by 1 minus r. Here a is the first term and r is a common ratio. The important point to note is that modulus of r should be less than 1, that is r should lie between minus 1 and 1. Its value should not exceed 1, otherwise we cannot use this formula. So the sum of infinite geometric series is equal to a divided by 1 minus r. So based on this, let's solve an IIT problem which appeared in 2004. It says that an infinite GP has first term x and the sum equal to 5. Then x belongs to, option number A is x is less than minus 10, option number B is x is greater than minus 10 and less than 0, option number C is x is greater than 0 and less than 10, and option number D is x is greater than 10. So in this problem we have been given an infinite GP in which the first term is x and the sum of all the terms is equal to 5. We have to find out the range to which x belongs, and we have been given the 4 options. So again let's look at the solution. Given to us is that the first term is equal to x and the sum of the terms is equal to 5. Let us say that the common ratio is equal to r and r is greater than minus 1 and less than 1, infinite series. So 5 is equal to x upon 1 minus r, as the sum is equal to a upon 1 minus r and a is equal to x here and r is equal to r. So 1 minus r would be equal to x by 5, or we take r to this side and x by 5 to this side to get 1 minus x by 5 equal to r. Now we also know that r should lie between minus 1 and 1. Therefore 1 minus x by 5 is greater than minus 1 but less than 1. We take 1 to this side and 1 to this side of the inequality to get minus x by 5 greater than minus 2 and less than 0. We multiply this inequality by 5 to get minus x greater than minus 10 and minus x less than 0. Further, this could be written as x is greater than 0 and less than 10. And so we can say that option number C is correct. Now let's solve one more IIT problem, and this appeared in 1991. It says that if S1, S2, S3 and so on up to Sn are the sums of infinite geometric series whose first terms are 1, 2, 3 and so on up to n, and whose common ratios are 1 by 2, 1 by 3, 1 by 4 and so on up to 1 by n plus 1 respectively, Then find the values of s1 square plus s2 square plus s3 square and so on up to square of s of 2n minus 1. So we have been given s1, s2, s3 and so on up to sn are the sums of infinite geometric series whose first terms are 1, 2, 3 and so on up to n, and whose common ratios are 1 by 2, 1 by 3 and so on up to 1 by n plus 1. And we have to find out the value of this expression. So let's see the solution of this. S1 would be equal to 1 plus 1 by 2 plus 1 by 2 square plus 1 by 2 whole cube and so on, because the first term is 1 and the common ratio is equal to 1 by 2. Similarly, S2 would be equal to 2 plus 2 by 3 plus 2 into 1 by 3 whole square plus 2 into 1 by 3 whole cube and so on up to infinite terms. This is because the first term of this series is 2 and the common ratio is equal to 1 by 3. Similarly, S3 would be 3 plus 3 by 4 plus 3 into 1 by 4 whole square plus 3 into 1 by 4 whole cube and so on, because again the first term here is 3 and the common ratio is equal to 1 by 4. So Sn would be equal to n plus n by n plus 1 plus n into 1 by n plus 1 whole square and so on up to infinite terms. Again the first term here is equal to n and the common ratio is equal to 1 by n plus 1. All this is given in the problem. Now we find the value of S1. We use the formula that sum of infinite terms is equal to a upon 1 minus r, where a is the first term and r is the common ratio. So for S1, a is equal to 1 and the common ratio is 1 by 2. Therefore this would be equal to 1 upon 1 minus 1 by 2. This comes out to be equal to 2. Similarly, S2 would be equal to 2 upon 1 minus 1 by 3, and this is equal to 3. S3 is equal to 3 upon 1 minus 1 by 4, which is equal to 4. And so we can say that Sn is equal to n upon 1 minus 1 by n plus 1, and this comes out to be equal to n plus 1. Thus the value of S1 is equal to 2, S2 is equal to 3, S3 is equal to 4 and so on up to Sn, which is equal to n plus 1. Now S1 is 2, S2 is 3, S3 is 4 and Sn is equal to n plus 1. Now S1 square plus S2 square plus S3 square and so on up to square of s of 2n minus 1 would be 2 square plus 3 square plus 4 square and so on up to 2n whole square. Now we also know that the sum of 2n square would be equal to 1 square plus 2 square plus 3 square and so on up to 2n whole square, and this would be 2n into 2n plus 1 into 4n plus 1 whole divided by 6. Now an important formula to notice that the summation of n square is equal to n into n plus 1 into 2n plus 1 whole divided by 6. We are going to study about this formula in the upcoming lectures, but for now let's use this formula and get the value of summation of 2n square equal to 2n into 2n plus 1 into 4n plus 1 whole divided by 6. And so we can say that S1 square plus S2 square plus S3 square and so on up to square of s of 2n minus 1 is equal to n into 2n plus 1 into 4n plus 1 whole divided by 3 minus 1. Simply this would be equal to summation of 2n square minus 1, and this would be equal to this term minus 1, which is n into 2n plus 1 into 4n plus 1 whole divided by 3 minus 1. Thus the value of S1 square plus S2 square and so on up to square of s of 2n minus 1 comes out to be this value. Now let's see another type of a series which is known as the arithmetico-geometric series. Now what is an arithmetico-geometric series? A series each term of which is formed by multiplying the corresponding terms of an AP and a GP is called an arithmetico-geometric series. So this series is actually formed by multiplying the corresponding terms of an AP and a GP to form an arithmetico-geometric series. Let's try to understand this definition. Let us say that we have a series in which the terms are a1, a2, a3, a4 and so on up to an, and this series is an AP. So we have an arithmetic progression in which the n terms are a1, a2, a3, a4 and so on up to an. Similarly, let us say that we have another sequence b1, b2, b3, b4 and so on up to bn, such that this is a geometric progression. So all these terms are in geometric progression. Now if we multiply a1 by b1, a2 by b2, a3 by b3, a4 by b4 and so on up to an by bn, then we get the series as a1 b1, a2 b2, A3 B3, A4 B4 and so on up to AN BN. And this series is known as the arithmetico-geometric series. We multiply the corresponding terms of AP and GP together to form the terms of a series, and this series is known as the arithmetico-geometric series. Let's see the general form of an arithmetico-geometric series. The general form would be S equal to A plus D into R plus A plus 2D into R square plus A plus 3D into R cube and so on up to A plus n minus 1 into D into R to the power of n minus 1. Here we see that A plus D is an AP, this term is an AP, A plus 2D is also in an AP, A plus 3D is an AP, and A plus n minus 1 into D is an AP. These are the general forms of terms which are in AP. Similarly, R would be a GP, R square would be a GP, R cube would be a GP, R to the power of n minus 1 would be a GP. This term is the multiplication of an AP and a GP. So we see that this term is the multiplication of a term in AP and the multiplication of a term in GP. Similarly, this is a term in AP, this is a term in GP, this is a term in AP and this is a term in GP again, and so on up to this term. So the general form could be written as A plus D into R plus A plus 2D into R square plus A plus 3D into R cube and so on up to A plus n minus 1 into D into R to the power of n minus 1. This is the sum of all these terms which are in arithmetico-geometric series. This is a general form of an arithmetico-geometric series and we are finding the sum of all these terms. Now when D is equal to 0, if we substitute D equal to 0, then what we get? We get S equal to A plus A into R plus AR square plus AR cube plus A into R to the power of n minus 1, and we see that this is actually a GP. Thus if we put D equal to 0 in this arithmetico-geometric series, then we get a GP whose common ratio is equal to R. Similarly, if we put R equal to 1 in this arithmetico-geometric series, then what we get? We get S equal to A plus D plus A plus 2D plus A plus 3D and so on up to A plus n minus 1 into D. And what we see? That this is an AP. Thus, when we put R equal to 1 in the arithmetico-geometric series, we get an AP. And when we put D equal to 0, we get a GP. Thus, arithmetico-geometric series is actually a combination of an AP and a GP. For example, if we consider the series 1, 4, 12, 32, 80, now what kind of a series is this? We can write this series as 1 into 1, 2 into 2, 3 into 4, 4 into 8, 5 into 16. Now again, what is so special about this? We take the first term and these are 1, 2, 3, 4 and 5. And what do we see? All these terms are in AP. Similarly, we take the second terms and they are 1, 2, 4, 8, 16, and we see that all these terms are in GP. Thus we see that all these terms are actually the product of corresponding terms which are in AP and in GP. 1 into 1, 2 into 2, 3 into 4, 4 into 8, 5 into 16. And so this series is an example of arithmetico-geometric series. We've just seen what is an arithmetico-geometric series. Now let's try to study the method to find out the sum of n terms of an arithmetico-geometric series. So let us say that we have an arithmetico-geometric series as S equal to A plus D into R plus A plus 2D into R square plus A plus 3D into R cube and so on up to A plus n minus 1 into D into R to the power of n minus 1. And let us say that this is equation number 1. S denotes the sum of all the terms which are in arithmetico-geometric series. Next, we multiply both sides of this equation by R, and what we get? R is equal to AR plus A plus D into R square plus A plus 2D into R cube plus A plus 3D into R to the power of 4 and so on up to A plus n minus 1 into D into R to the power of n. And let us say that this is equation number 2. We have written this in such a manner that this term coincides with this term coincides with this term coincides with this, and so on. Now we subtract equation number 2 from 1. What we get? We get 1 minus R into S in the LHS, and in the RHS what we get? A plus dr plus dr square plus dr cube and so on up to D into R to the power of n minus 1 minus this term remains a plus n minus 1 into d into r to the power of n. We see that if we subtract this term from this, what we get is dr. Similarly, we can subtract this term from this term to get dr square. We subtract this term from this term to get dr cube, and so on. Thus, we get 1 minus r into s equal to a plus dr square, and so on up to d into r to the power of n minus 1 minus this term, which is a plus n minus 1 into d into r to the power of n. Further, we see that this is a GP in which the first term is dr, common ratio is r, and the number of terms is actually equal to n minus 1. So the sum of all these terms would be dr into 1 minus r to the power of n minus 1 whole divided by 1 minus r. So we write this equation as 1 minus r into s equal to, this term remains the same, a plus the summation of this becomes dr into 1 minus r to the power of n minus 1 divided by 1 minus r minus this term, which is a plus n minus 1 into d into r to the power of n. Now what we do is we divide both sides by 1 minus r. Thus s is equal to a upon 1 minus r plus dr into 1 minus r to the power of n minus 1 whole divided by 1 minus r square, because we divide by 1 minus r, minus a plus n minus 1 into d into r to the power of n whole divided by 1 minus r. And this is actually the formula for sum of n terms of an arithmetic or geometric series. Now, when modulus of r is less than 1 and n tends to infinity, we take the case that modulus of r is less than 1 and n tends to infinity, that is, it becomes an infinite arithmetic or geometric series. Then in this condition, r to the power of n minus 1 would tend to 0, and also r to the power of n would tend to 0. Thus s would become a divided by 1 minus r plus dr into 1 minus 0 whole divided by 1 minus r whole square minus a plus n minus 1 into d into 0 divided by 1 minus r. This term becomes 0, this becomes 1, and so what we get is s equal to a divided by 1 minus r plus dr divided by 1 minus r whole square. So this is the formula when modulus of r is less than 1 and n tends to infinity, that is, the number of terms is infinite of an arithmetic or geometric series, and also r lies between minus 1 to 1. Now based on this, let's try to solve an example. Find the sum of first n terms of the sequence 1, 22, 333, 4444 and so on. That is 1, 2, 2, 3, 3, 3, 4, 4, 4, 4 and so on. So the terms are 1, 22, 333, 4, 4, 4, 4 and so on. So we can write this as 1, 2 into 11, 3 into 1, 1, 1, 4 into 1, 1, 1, 1 and so on. Further, now we can write all these terms as, the first term could be written as 1 into 10 to the power of 1 minus 1 divided by 9. This term could be written as 2 into 10 square minus 1 divided by 9. This term could be written as 3 into 10 cube minus 1 divided by 9 and so on. Further, this becomes Sn equal to 1 into, if we add all these terms, then Sn would be equal to 1 into 10 to the power of 1 minus 1 whole divided by 9 plus 2 into 10 square minus 1 divided by 9 and so on up to n into 10 to the power of n minus 1 divided by 9. Further, this could be written as 1 by 9 into 1 into 10 plus 2 into 10 square and so on up to n into 10 to the power of n minus 1 plus 2 plus 3 and so on up to n. We have actually split it into two parts. The first part contains these terms and the second part contains these terms. This is an arithmetic or geometric series in which d is equal to 1 and r is equal to 10, and the value of this is equal to n into n plus 1 divided by 2. Thus we use the formulas to get the final value of Sn equal to 1 by 9 into n into 10 to the power of n plus 2 minus n plus 1 into 10 to the power of n plus 1 plus 10 whole divided by 81 minus n into n plus 1 divided by 2. Let's try to solve one more example. Find the value of 2 to the power of 1 by 4 into 4 to the power of 1 by 8 into 8 to the power of 1 by 16 into 16 to the power of 1 by 32 and so on. So let's look at the solution of this problem. Let us say that S is equal to 2 to the power of 1 by 4 into 4 to the power of 1 by 8 into 8 to the power of 1 by 16 and so on. This could be further written as s equal to 2 to the power of 1 by 4 into 2 to the power of 2 by 8, because we know that 4 is equal to 2 square. Similarly, this could be written as 2 to the power of 3 by 16, because 2 cube is equal to 8. And this could be written as 2 to the power of 4 by 32, and so on. Further, we can write this as s equal to 2 to the power of 1 by 4 plus 2 by 8 plus 3 by 16 plus 4 by 32, and so on up to infinite terms. Now what we are going to do is, we take s dash to be equal to 1 by 4 plus 2 by 8 plus 3 by 16 plus 4 by 32, and so on. We are going to first find out the value of this sum, and then we'll be able to find out the value of s. So s dash is equal to the sum of these terms, and let us say that this is equation number 1. Now what we observe here is that this is an arithmetico-geometric series in which we see that d is equal to 1 and r is equal to 1 by 2. So what we do is, we multiply both sides of this equation by r, which is equal to 1 by 2. Thus this becomes 1 by 2 s dash equal to 1 by 8 plus 2 by 16 plus 3 by 32, and so on. And let us say that this is equation number 2. We have written this in the form that this term coincides with this term coincides with this term coincides with this term, and so on. Now we subtract equation 2 from 1. What we get? S dash by 2 equal to, this term remains the same, 1 by 4. When we subtract 1 by 8 from 2 by 8, what we get is 1 by 8. Similarly, when we subtract 2 by 16 from 3 by 16, we get 1 by 16. This becomes 1 by 32, and so on. So s dash by 2 is equal to 1 by 4 plus 1 by 8 plus 1 by 16, and so on. Now we can clearly see that all these terms are in GP, and this is an infinite geometric progression. And also we know the formula for finding sum of the infinite terms of an infinite GP. This is equal to a divided by 1 minus r. Here we see that a is equal to 1 by 4 and r is equal to 1 by 2. Therefore, we use that formula to get s dash by 2 equal to 1 by 4 whole divided by 1 minus 1 by 2. This becomes equal to 1 by 2. And so we get s dash equal to 1. Thus the value of 1 by 4 plus 2 by 8 plus 3 by 16 and so on is actually equal to 1. And thus when we substitute this value in this expression, we get the value of s equal to 2. Thus 2 to the power of 1 by 4 into 4 to the power of 1 by 8 into 8 to the power of 1 by 16 into 16 to the power of 1 by 32 and so on is actually equal to 2. So this was all about what is a geometric progression, what is a general term of a geometric progression, what is the formula for finding the sum of n terms of a geometric progression, and also how to find the sum when the geometric progression is infinite. Also we have seen a special type of series, which is the arithmetico-geometric series, in which we have seen how to find the sum of n terms of this type of special series, which is the arithmetico-geometric series.